Hello everyone, my name is Chen. Today I would like to present my work for CS239, a clip-based image generating model. At the very beginning of this year, OpenAI has published a vision language model named Clip, which has drawn huge attention in both academia and industry. The model learns a visual and text representation jointly using constructive laws and has shown promising capacity in various downstream tasks, like zero-shot classification, text-to-image retrieval, etc. Motivated by it, my work proposed a generative model based on clip visual and textual encoders for image generation. It demonstrates capacity of 1. Free query image generation, 2. Conditional image style transfer, 3. Out-of-distribution style transfer. Let's have a brief review of what Clip does. It trains an image encoder and a text encoder together to predict the correct pairing of a batch of image-text training examples using their embedding in the same latent space. As a consequence, it managed to arrange image and text with the similar semantic meaning to have closer distance in the latent space. In this work, we used the pre-trained OpenAI Vision Transformer base 16 image encoder and text encoder, and our training objective is to train an image generator to reconstruct the image directly from the clip image embedding. Thanks to the nature of clip, the trained image generator is expected to understand the semantic meaning of any embedding, either it's image or text, or it's a mixture, as long as it's encoded in the same clip latent space. Note that the main difference between the current work and the standard generative model is, instead of sampling from a prior distribution PZ, we simply rely on the predefined latent space distribution of clip for the sake of visual language semantic similarity. Here is how we train such an image generator with clip encoders. In the training time, we first pass the image to the clip image encoder to obtain its embedding Z. Then we train an image generator along with an image discriminator to reconstruct the original image. While the discriminator minimizes the gain hinge loss, the generated loss is composed of two components. One, the reconstruction loss including pixel and perceptual wise loss. 2. The standard gain loss with an adaptive weight. This weight is defined as the ratio between the gradient of reconstruction loss and the gain loss, and it can balance out the two terms in this generated loss. The entire training methodology is inspired by both VQ gain and geometric gain. In the inference time, depending on which task it is, we use the clip image and text encoder to map the source to the clip latent space. Then we feed it to our trained image generator for image generation. Now let's discuss the experiments. The first task we tried is simply image reconstruction. We trained a generator first using high-resolution celebrity face dataset. Then we checked the reconstruction quality of the image from its original image clip embedding. For comparison, we feed three versions of image to the generator. 1. The original 256 by 256 version. 2. A resized 16 by 16 version. 3. A random masked version. We can see the reconstructed image do preserve high-level information of the original image, but not in great details, like texture or face orientation. This phenomenon is more obvious for resized case. This is mainly due to the fact that clip image encoder introduces information loss when encoding the image into its latent space. So the construction has no access to the lossless information of the original image. This is one of the limitations of the current approach of using clip, but meanwhile, we did gain the ability of playing around the embeddings in the latent space, which you will see in the following experiments. The second experiment we have is image interpolation. The idea is very similar to other standard generative model, but again, it's by clip encoders. The procedure is to take any two images, compute their clip embeddings as Z1 and Z2, then compute weighted average between these Z1 and Z2. Let's call the new embedding as Z prime. Then we feed this Z prime to the generator, and then we can see that it produces smooth transition from one image to another image, and all of them are with high fidelity. The next experiment we have is free query image generation. Namely, it is to generate image from free query text. How it works is we feed the query text to the clip text encoder to get its text embedding. Since it's living in the same space as the image embedding, we can direct feed it to our generator. Here we illustrate 4 different examples as shown in the poster. We can first see the generator is able to generate image that captures a variety of semantic meanings, like skin color, face emotion, and wearings, so on and so forth, and then produce the corresponding images. The fourth experiment we have is called image style transfer. The idea was borrowed from the analogy property of embedding in NLP's domain. For example, king equals queen minus woman plus man. Here we wish to insert certain style into the given image. To achieve this, we define a text-based style prompt. It is to take 2 strings, a style string like a happy person, and a base string like a person. We feed both of them into clip text encoder to get their embedding and do subtraction in the latent space. This will somehow give us a concept of happiness in the latent space. Then we do interpolation between this prompt and the image embedding we obtained from the source image fed into clip image encoder. At the end, we pass the weighted embedding into the generator, and this will give us the image with the style we want. As you can see, here we've shown 6 different style examples with 4 different persons, and all of them looks good. The last experiment we have is the out-of-distribution style transfer. The main idea was since clip can encode the semantic meaning of an image into its latent space, no matter the image is in anime or real photo, we can take advantage of this property to do style transfer with image that is out of our generator's training data. Here is how we perform 2 experiments. One is from anime to real person. 2 is from real person to anime. For the first one, the model is trained using celebrity face dataset, but we feed anime face dataset in inference time. The second one is effectively the other way around. To achieve slightly better quality, we also apply the text prompt trick that we introduced in the last experiment. And you can see the result on the right hand side. Last but not least, we compare our model with other text-guided generative models using celebrity face dataset, and you can see our model gives the best FID scores. Here is the end of my presentation. Thank you.